Hi, everyone. Thank you so much for joining us today. My name is Ruth Favela, and today I'm excited to be chatting with Max Green, one of our data scientists at tomorrow.io. Today, Max and I are discussing an interesting topic. We're talking about the power of machine learning in wind energy forecasting. Max, thanks so much for being here. Could you start us off by introducing yourself and telling us a little bit about your role at tomorrow.io?
Yeah, for sure. Yeah, thanks for having me, Ruth. Hello, everybody. As Ruth mentioned, my name's Max Green. I'm a data scientist here at Tomorrow.io, and I work on the data science team under Tyler McCandless, and I produce sort of derivative energy products using machine learning that are based on underlying weather forecasts that Tomorrow.io produces. And so I basically take the weather and then try and predict other things that result from weather in the energy sector. So today we'll be talking about the wind power product.
That's great. At Tomorrow, we're doing a lot to advance weather forecasting. And today we want to highlight one area where we're continuing to innovate and make progress. Max, do you want to set the scene a little bit for us? Can you tell me what tomorrow.io is doing to advance wind energy forecasting specifically?
Yeah, absolutely. So yeah, this is a really interesting field right now. There's a lot of cool data-driven machine learning work that's happening in general in the energy space. But Tomorrow.io is focused on wind power forecasting because it's one of the most rapidly growing renewable energy sources currently. And so we started this project maybe about a year ago, and our scientific goal is to essentially forecast wind power at a wind farm spatial resolution across the entire United States and in Alaska. And eventually we'll scale that up to a global level. And so right now we are producing hourly forecasts rolling out 2 days across every synchronized wind farm in the United States. And what that looks like is a forecast of megawatts. So basically, based on the weather conditions, how efficient do we think every single wind farm in the United States is going to be for the next 48 hours? And what electricity can we expect that farm to dispatch to the grid?
That's really interesting. And it's also really important because, like, as you said, wind energy is a really big thing in the US. I was actually just reading that wind energy specifically supplies 10% of total US electricity. And that's like literally one tenth of total electric needs in the US. So I can really see how this would be valuable. Can you talk to us about what makes tomorrow.io unique in the wind energy forecasting industry?
Yeah, absolutely. Well, I think we sit in a really unique position here because, Tomorrow.io is a primarily a weather forecasting company. So we have all of these proprietary advanced weather models, and those serve as an input to the wind power model. And so we sort of already start kind of a step higher because we have this really high quality wind forecast and atmospheric dynamics forecast that we then can pump into a wind power machine learning model. And so that's one way in which we stand out. And then we also sort of differ from competitors in this space because we're focused on finding the correlation between historic observations, so what actual wind farms dispatch to the grid historically, and forecasted weather conditions. And that allows us to bias correct for any, uncertainty that may be present in the weather forecast itself by pairing it with what actually happened on the ground. And that's where the machine learning really comes into play. It allows us to really create a nice tight fit model that can explain the variance that is present between those two things.
So, how are we specifically using machine learning in that whole system?
Yeah. So the machine learning sort of sits right in between the historically observed power dispatch and the historically forecasted weather. So let's say, one scenario is in West Texas, there's forecasted to be a strong northwest wind, coming in at around, 17 meters per second. That's a strong wind. And historically, we've seen that during those types of conditions, there's, about 60% efficiency from most wind farms in West Texas. So let's make this a little bit more complex and start to oscillate the humidity, which changes the density of the actual air. So the machine learning model will allow us to incorporate the impact that attributes like humidity or air pressure uh, and wind direction have on the actual power that gets dispatched. So historic methods that only take wind speed and pump that through a physics-based power curve are going to lose out on the nuances that the other components of the atmosphere will impact power generation.
Can you explain to us how probabilistic techniques are used in improving the accuracy and reliability of weather forecasts? And like maybe before that, you can explain to us what probabilistic forecasting is?
Yeah, absolutely. So yeah, super good question. This is like another way that I think our product is a little bit different than our competitors and than what is currently available on the market. Traditional deterministic, or I guess like non-probabilistic machine learning techniques exclusively are trying to model the most likely outcome in any given scenario. And so that's going to be, we think that wind farm A is going to produce, 90 megawatts of electricity at 9 a.m. Now, the reality is there's many different potential outcomes of what could happen at 9 a.m. And those outcomes are related to, well, maybe the wind speed was improperly forecasted, or maybe there's, a human operator has to make a decision to say, okay, we're going to have all wind turbines running, or we're going to have half the wind turbines running. There's lots of different parts of this puzzle that can change. And so a probabilistic model allows us to quantify how likely these different outcomes are. And so instead of just having that 90 megawatts at 9 a.m., we have what's probably going to happen is 90 megawatts at 9 a.m., but it could also be as low as 30 megawatts or 110 megawatts, depending on what the actual weather forecast looks like. So, by providing a probabilistic forecast, we're allowing the users to have a sense of uncertainty in how uncertain that most likely scenario is to actually occur.
That was really interesting and really helpful in helping understand like what probabilistic forecasting is. In simple terms, can you explain to us how machine learning helps us predict the weather more accurately than traditional forecasts?
Yeah. So, I think that, machine learning and traditional weather forecasts really kind of at this moment go hand in hand.
Mhm.
Right? The traditional weather forecast models are physics based, they're numerical differential equations based on first principles, and they're, excellent and they have great skill scores. There are limitations to their use, right? There are spatial and temporal limitations to their use, and machine learning can allow us to sort of bridge the gap a little bit by leveraging historic data observations and fine tuning what the traditional forecasts would produce.
Okay, that's awesome. Are there any challenges when using machine learning for prediction for weather predictions? How do you overcome those, and what are they?
Yeah, I mean, so that's a great question. The age old limitation is training data set quality and quantity. And so in the wind power prediction problem, that's certainly a limitation that we struggle with, and it's getting better and better over time as those historic data sets are growing in size and in quality. But something that we spend a lot of time doing here at Tomorrow IO is quality controlling and cleaning those historic data sets, because we want to make sure that periods when a wind farm was offline, or when a turbine was being worked on or cleaned. Like, we don't want that type of event to impact the model that we're training, or the correlations that we're trying to learn between the weather and the power output. And so that's a great challenge right there. Is like, it's a massive data set, and we have to spend a lot of time going through it and understanding the different impacts that may be at play.
So you guys are just manually doing all the work essentially.
Yeah, we're kind of combing through, looking at the patterns, correlating it with lots of different reports that say, a wind farm was limited at this from this hour to this hour. We want to pull those periods out of the data set, make sure the model isn't exposed to that. So yeah, stuff like that, pulling lots of different data sets together to try and get
Mhm.
a large global picture of what was happening on the grid, basically at every hour in a, 5 to 7 year period.
That's really cool. Why don't we talk a little bit about our findings and the data and our models and that kind of thing? Could you explain to us how our modeling outputs compare to widely available data sets currently?
Yeah. So, one of the sort of benchmark comparisons that proprietary wind energy or wind power forecast would make is by comparing a regional or system level aggregation of the forecasts to what the actual grid forecasted, right? Because the grid they produce forecasts at an hourly cadence because they have to understand themselves how much wind power they can expect. And so our, benchmark is to basically compare our forecast to their forecast. And in many cases, we're comparable or exceeding the quality of their forecasts. We make comparisons to the ERCOT ISO, to the SPP ISO, to the Midwestern ISO, basically to all 7 competitive markets in the United States. So we're constantly assessing, on a real time basis, like, oh, there's a crazy weather event happening in New England. Like, what's our outlook look like compared to the New England ISO? And then after a 2-day period, we'll do a retrospective study and compare both forecasts against what actually happened.
Yeah, and then I know we just published some content around findings in recent storms Finn and Heather. Can you tell us a little bit about why that was profound for tomorrow.io?
Yeah, absolutely. So Finn and Heather were 2 recent winter storms that cropped up throughout pretty much all of Texas. And, you know, every winter now, Texas is having 1 or 2 more severe weather events. And it can leave the ERCOT ISO or the Texas power grid in a really vulnerable position. The consequence of misforecasting solar or wind dispatched to the power grid can be an over reliance on those renewables and then a last minute call to more expensive power like natural gas or coal. And so that can cause 2 different problems. One, it can create a large spike in electricity because now there's a scarcity, right? We thought there was going to be 40% of electricity provided by wind, but in reality, there's only 10. So then there's a 30% gap. How do we make that up? We make that up by immediately burning more fossil fuel based resources. And so that can cause price spikes that fall down to the consumers, or in the worst case scenario, actual like rolling outages in which there isn't enough power to serve the population and certain areas have to experience rolling blackouts. And luckily, during Finn and Heather, those consequences were not observed, but historically, it's always a possibility. And during that period, our wind power forecasts came out incredibly accurate, and so did our temperature forecast. Temperature is a great indicator of demand, right? If it's really cold, then people are going to be using heats and other electrical devices throughout the weather event.
Yeah, that makes sense. Last question for you. How are we evaluating the performance of machine learning models to demonstrate a successful wind power forecasting product?
But that's a great question, Ruth. Thanks. Uh, At a regional and system level, we can make a daily comparison against the actual observed power dispatch. And then at a nodal level, so at the actual resolution of a wind farm, we just have to wait 2 months. And then that data is published by the power grid in Texas, and we can directly compare our finest resolution forecast to what was actually observed. And so we have a process in place in which we are continuously assessing the model performance on a rolling basis and are monitoring for any, substantial errors. But so far, so good. We've gotten a lot of excellent feedback from beta testers and clients that are currently using the forecast.
Cool. Yeah, that makes sense. So, moving on a little, for those of us not in energy trading, can you tell us about the application of wind energy forecasts? Who uses them and where do they make a difference?
Yeah, absolutely. So the sort of use case for this forecast basically falls into 2 different groups. One is a quantitative energy trader. Let's say energy traders can work for wind farms. They can work for banks or for large trading firms. So there's markets that exist to facilitate the balance of supply and demand of electricity that are sort of similar to stock markets. And so traders have the ability to buy and sell power in a day ahead market. And that basically creates the most economically viable plan to schedule all of the different resources that need to fill the needs of the power grid. And so those traders will use the wind power forecast to inform their positions on an hourly basis. Grid
Okay.
operators, on the other hand, are directly involved in scheduling the power as it's being dispatched. And so they'll use the forecast in a similar way, right? We can expect 20% of the power demand to be met by wind for tomorrow. So we'll use we'll schedule natural gas or coal to fill in that 80% gap. That's sort of the scenario in which they're using that information.
I understand that there are some regions that might have more challenging weather to predict. Can you speak to our experience forecasting in regions with high variability? I'm thinking of places like Alaska, for example. What are we doing for regions like that?
Yeah, that's a super great question. And Alaska is a good example of that. Alaska poses a really unique and rugged landscape that creates really complex wind and weather events. The combination of coastal winds, mountainous terrain, and the upwelling that can occur from that just creates a lot of different dynamics that are hard to forecast for. And so currently we're forecasting for 33 different farms in Alaska. And this is where, this particular type of problem is exactly where machine learning poses a great solution because we can pair the forecasted weather with actual observed power dispatch. And that allows us to sort of bridge the gap between error that might be present in the forecasted wind speed and our derivative power forecast.
Do we approach every region that might be more challenging in a similar way?
We'll approach it not in the same exact way, right? Like each region, if it's substantially different, we'll have a different model that allows it to fit better to that particular area, right? Because we want models to be as general as possible while limiting, the amount of overgeneralization that happens. And so places like Alaska have a really unique microclimate. We want to really hit the nail on the head and optimize our model by looking at exactly those correlations.
Gotcha. Well, thanks for explaining all that, Max. I have a couple more questions and then we can wrap this up. Well, looking forward, how do you see the role of machine learning in weather forecasting evolving in the next few years?
Yeah, that's a really great question. And I think one that, lots and lots of folks are asking right now. I think as larger and more complete historical data sets crop up, we'll see larger and larger models that can capture more and more variance present in weather forecasts. And so I think, the two main areas for improvement right now are, of course, enhanced accuracy and then also enhanced spatial resolution. So how small, how far can we zoom in on space and understand how, neighboring points in space may differ? And then further, a reduction in latency, and that's probably a reduction in the amount of time it takes to produce a forecast, right? And so as computer chips become more efficient and compute times go down, then we'll see a faster and faster forecast update rate.
What about the role of weather and machine learning in the energy industry? Where do you see that heading? Do you think it could advance the ability to integrate renewable energy into the electric grid?
Yeah, absolutely. I think that having really accurate, data driven renewable energy forecasts is a critical component in electrifying the grid and in becoming more and more reliant on renewable resources in particular. Right. And it all comes back to being able to answer the question, how much electricity can we expect to come in from wind and solar so that we can minimize the amount of electricity that we use from fossil fuels? And so, as that answer becomes more and more clear, then we can start to become more and more reliant on renewable resources since they're intermittent. We can't just crank the wind up and get more power, right? We can do that with coal and natural gas, but that's expensive and has a lot of negative implications.
Gotcha. Well, thank you so much, Max. This has been really educational, and I'm excited to keep learning. Thank you all for watching, and we'll see you all next time.
Thanks, everybody. Thank you, Ruth.